here's the last subject in 3.5, rational function models. So we're finding the traffic intensity of a rational function. So this is like a parking garage, and you're figuring out how many people are waiting in line at any given time, and so vehicles randomly arrive, and they arrive at a rate of 2.6 vehicles per minute, and the parking attendant can let 3.2 vehicles through per minute. They are random though, so they do come in various times, so we want to figure out the traffic at intensity, and that is defined by the ratio of the average arrival time over the admittance rate. Okay, so to find that, we want to find that, then traffic intensity. And so we take the average arrival rate, which is 2.6, and divide that by the average admittance rate, how many we let in per minute, which is 3.2. So take 2.6 and divide that by 3.2, and we get approximately 0.8125. And so that is our traffic intensity, is 0.8125. Okay, and then to find the average of number of vehicles waiting in line, given the traffic intensity, is the function f of x equals x squared over 1 minus x. So that's minusing x, so that's a little different from maybe what we've done with. Usually do x minus 1 or something like that. So you could get rid of that by multiplying the top by negative and the bottom by negative, and that would, well, basically you're just moving the negative from the bottom to the top, which is fine, because it doesn't matter if it's like negative 1 over 2 is the same thing as 1 over negative 2. So if you take out that negative from the bottom, you can just move it to the top. So it could look like this: negative x squared over 2 times x minus 1. And that would be the same thing. I just basically divided out a negative on bottom and I put it on top. So those are the same thing. So we want to go ahead and graph this function. You can graph either one here, that's fine. So let's go ahead and graph that. Okay, so we go ahead and graph this. First we find the vertical asymptote. That's setting the denominator equal to 0. And so it's basically 2 minus 2x equals 0. Add 2x, so we get 2 equals 2x. So x is equal to 1. And we're not going to cancel any factors out of top because it's just x on top. So there's our vertical asymptote or horizontal asymptote. Right, we see which denominator or degree is bigger, the numerator degree or the denominator degree. Okay, and the numerator degree is bigger, so that means we're going to have a oblique asymptote. All right, so we're going to have to do synthetic division or long division here because it's 1 minus x, and because we're multiplying by a factor of 2 on bottom, right, it's 2 times 1 minus x, or 2 times x minus 1 if it's a negative x squared on top. So here it would be best to probably do long division. You can do synthetic division, but you run in kind of some problems because we have, if we did the negative x on bottom, what goes in the box would still be 1, and you'd have 1, 0, 1, 0. So 1, 1, 1, right? So you get x plus 1 is your oblique asymptote or slant asymptote. But because that's a negative x, you're going to have to multiply this by a negative, so you get negative x minus 1, and because you have a factor of 2 on the outside, you would have to divide these by 2. So there you go. Or you can do long division, which would be 2 negative 2x minus 2 if you write it in standard form, and then x squared goes in here, so then you have a 0x, and then you have a constant 0. And you multiply, what do I have to multiply negative 2x by to get to an x squared? That's an x 1/2, and actually negative 1/2 x, so you get a positive x squared here. And then when you multiply it by negative 2, you get a positive x, and then you subtract those, and so we get an x squared. Actually, that is a negative. Yeah, there we go. So we get 0 here, and we get negative x. Then what do I have to multiply that by? That is a negative again, and negative 1/2. So negative 1/2 times a negative 2x is a negative x, or positive x. Okay, oh, and then if I subtract, that's actually not going to cancel out, right? So come back here, this is actually a positive 2, right? Because it's 1 minus x times 2. So it's actually positive 2. That's still negative still, so you get a positive x here, you get a positive here. That's why this has to be negative here. So then you get a positive. Then you got to subtract them. So I subtract them, I get 0x. And so there you can see it's the same as this one. So there's our oblique asymptote or slant asymptote, and so then we can graph those. Okay, so let's go ahead and graph those. Vertical asymptote through x equals 1. Oops. X equals 1. Then we have our slant asymptote at negative 1/2 minus 1/2, right? Y equals negative 1/2 x minus 1/2. So I go down 1/2. I go down 1/2, and then I go down 1 over 2. So down 1 over 2 will be right here, and that's going to be my slant asymptote. So through those 2 points, let's see. It's probably pretty good. Okay. And then again, we don't actually have points there. Okay, then we go ahead and set negative 1/2 x minus 1 equal to see if it crosses that slant asymptote there. Okay, so we take that and then we multiply both sides by the denominator, which is going to take out that one. So we get 2 minus 2x. We're going to go ahead and FOIL this out. You can see what's going to happen. We're going to get an x squared on both sides. Right, so when we multiply these two, we're going to get a negative x squared. Or sorry, no, that's fine. This part right here is where we're going to get a positive x squared. So we're going to get a positive x squared when we do inside times inside, and then on this side we have an x squared. So those are going to cancel out, right? So this is not going to cross because we're going to get like 1 equals 0 or something like that. Okay, so those are going to cancel out, so it's not going to cross this. So now we can go ahead and test plug in 2 and see what we get, and plug in 3, plug in 0. When we plug in 0 right here, we know we're going to get 0 on top, so there's 0, 0 is a 0.00. We could plug in negative 1, see what we get, and positive 2 and positive 3, and then we can go ahead and graph this. Okay, so we plug in negative 1, square that, we get 1 on top, and then we get negative 1. So there's 2, so that's 4, so negative, so we get positive 1/4. So 1 was up here somewhere, so 1/4 at negative 1 stays there, so it's somewhere about right here. Okay, and then we can go ahead and plug in a positive 2. So 2 squared is 4. 2 times 1 minus 2, that's negative 1. So we get negative 2 over 4, which is a negative 2. So at negative 2, negative 2. So you can tell it's probably going to go something like that, something like this. But here we have negative y values, so that'd be negative people in line, right? So then here we probably want to actually, more information is probably we want this information right here. We want right here. This is the information that we want in this area, right? Because here we have positive x's, so that's you know, the traffic intensity, right, is your x value, and your y value is number of people in line. So we want right here, because this is negative x's, so we don't want that. This is negative y's down here, so we don't want that. So we're paying attention between 0 and 1, what's happening in between 0 and 1. And that's why the second part asks you to go ahead and plug in the point 8125 to figure out what that traffic intensity is. And so you can plug that in, and that is approximately 1.76 vehicles. So 1.76 vehicles is the traffic intensity. So that's how many vehicles are waiting in line when the traffic is most intense. Okay, so the last question, what happens when the number of vehicles waiting in line when the traffic intensity approaches 1? So as we get closer and closer to 1, what's happening? Right, so we get x squared over 2, 1 minus x. So as this gets closer and closer to 1 here, right, where it's undefined, so what's happening in our graph? The number, right, y is the number of vehicles waiting in line, so as we get closer and closer to 1, the traffic in line goes up and up and up and up and up and up and up. So the number of people is just overwhelming, right? The person, the attendant can't keep up with the number of people in line, so it keeps on increasing. So here's your homework page 356, number 113. And so here's the formula for that. And basically you're kind of doing the same thing, but luckily here you do not have a slant asymptote or oblique asymptote because the degree of the denominator is bigger because it's squared there. So you don't have to do synthetic division or long division there. Okay, so I'll go ahead and do this problem. I'll just basically read it to you, right? So you're at an amusement park, and the vehicles arriving at the gate of the amusement park is equal to k, and let the average number of vehicles emitted into the park is r. So the number of vehicles coming in is r, the number of vehicles arriving is k, the number of vehicles let in is r, and we want to know basically if on Saturday afternoon if k is equal to 25, how can we find our r if our t, the time we're waiting, is 30 seconds. So that's why a lot of these real world problems require calculators, so that's why in the problem it asks you to use a graphing calculator. So really if you have a graphing calculator you can plug this in, and we want to get to when t is equal to, so if k is equal to 25, we can enter that in. So our denominator is 2r squared minus 50r. Okay, and so we can plug that into the calculator and ask us, okay, when t is 30, what's our r? And our r is our x-axis, so this is r and this is t. So you could plug that into the graphing calculator and enter, and then do a calculate when t equals 30, find r. Or you could use a table, go down to 30 on your t and see what r is, what it's estimated to be. So the best thing to do is if you have a graphing calculator. If you don't, that's okay. I'm not going to do this problem fully. I'll do setting the denominator equal to 0, right? So here we can factor out an r. So we get, and a 2 as well. So we get r minus 25 equals 0. So that means r is equal to 0 and r is equal to 25. So those would be our vertical asymptotes at those places. We can check the top, see if we have a hole somewhere, and it's 2r minus k, so that is 2r minus 25. And so there, we don't have a common factor, right? Because it's 2r minus 12.5, right? So no common factors, so we can't cancel out. So r equals 0 is a vertical asymptote, and r equals 25 is a vertical asymptote. We want to find when t is 30, basically what is our r, right? So you could graph this. You could enter in 0, and then say this is 25, and we're trying to figure out r, or that's our t actually, so we're up here. That's our r is 25, and we want to find out if this was 30 for our t, what is our r, where is our r located? So the best thing to do is just have a graphing calculator and graph this out. You can use online, there's graphing ones that you can do. So I'll go ahead and show you actually how to do that. So here I can enter this function into an equation online and see what the graph actually looks like. So this is Oh, that's because I should have put an R here instead of an X. There we go. You got to have your variables consistent. Let's see. Okay, so I guess it's best to do X's on all these. So there's our function. I just turned the R's into X's, plugged in my K, which is 25. You can scroll down here. You can see, it gives you your asymptotes right here. 0 and 25. Horizontal is 0 because the denominator is bigger, right? And then you can come down here and you can see here's the graph. Horizontal asymptotes are two vertical types, and we want to know when t equals 30. So somewhere in here, so you can at least see the graph. I'm not sure if this, you can actually plug in numbers for t and actually find out what it is on this one, but at least you can see kind of what the graph looks like. Oops. So there's the graph. So you can look at when t equals 30, kind of what does our graph look like. So at least you could use something like that. There might be things that you can actually plug in your t and solve it into that. And then B, you find out 5.3 per minute, and so that would be that would kind of be your R, and so there's a little more to do with that. Alright, so we have graphed our vertical asymptotes. Now we can do our horizontal. So our horizontal, we look at the degree of the numerator over the degree of the denominator. The degree of the denominator is bigger, so y equals 0 is the horizontal asymptote. Now you could graph this. Now, so if you don't have a graphing calculator, you can graph this, but it still will be hard to actually find out what the answer is here. But we can go ahead and do that. If we plug in 5, that would be 5 minus 25, and 2 times 5 minus 25. And then on the bottom here, we would also have 2 times 5. So here we get negative 15 on top. On the bottom, we get negative 20 times 10. So that's negative 200. So if we divide that, we get a small decimal. It's positive though, so we're somewhere down here. If we want to see if it crosses, that we set this equal to our horizontal asymptote, which is 0. Multiply both sides, so we get just 2r minus 25 equals 0. Add 25 to both sides, divide by 2, so that's 12 and a half. So 5, 10, 12 and a half, so somewhere about right here it crosses. So we can kind of see that it's probably going to go up this way, and then probably crosses and comes down to this one. And we can tell that it kind of does that. If we plug in more numbers, we can see that. But we can see it's going to go up and to the left. The question is, does it come back this way? Okay, and so how we can tell that is to plug in more numbers. Okay, so if we plug in, say let's plug in, that's 5, 10, 15, 20, let's plug in 20. So let's go ahead and plug in 20 and see kind of what we get here. So let's erase this and plug in 20. So 2 times 20 minus 25, so that's 40 minus 25, so that's 15. And then 2 times 20, and then 20 minus 50, right? Because it's r minus 2. If we factor, or sorry, 25, not 50 here. 25. So we get a negative 5 here, and we get a 40 again here. So that's going to be negative 200. So it's the kind of opposite of that one, right? So somewhere right down here. So we can see it's going to go down. Remember, they always approach the asymptotes, right? The only time it crosses is when it's a horizontal asymptote, and we have to check that, which we already did. Okay, so since these are our factors, right, we have r. If we factor this out, we have 2r and r minus 25. So this has a factor, right there is 0, factor of 0, and here's a factor of 25, right? or a 0 of that. And so this factor right here has a degree of 1. This factor has a degree of 1. So what that means is if one side is going up on the vertical asymptote, that means on the other side of the vertical asymptote, my graph is going to go down. So that means this one is going to go down this way, and then it'll approach the horizontal, right? If this one's going down, because this asymptote here has a multiplicity of 1, right? 25 only occurs once. So that means if this left side's going down, the right side is going to go up, and that means this side is going to approach that horizontal asymptote. So there's the graph of it. Now what we want to know is where does it reach 30 at, right? 5, 10, 15, 20. So somewhere up here, where does it, what's the x value that reaches? So we see that's going to be a really small number, right? And 30 is 30, is it 30 minutes or 30 seconds here? I believe it's 30 seconds, right? So that's half a minute. So what we can do, a way to solve this, is set it equal to a half. And that's the way that you could solve this. 2r squared minus 50r, right? So you could set it equal to a half, and you could solve it that way. Another way to do this with your calculators is on your calculator, once you type in this formula or equation and you push graph, there's a table button, you hit table, and it gives the list of your x's and your y's. So what you go down is you scroll down until you get to 0.5, and then you look at the x value. And it turns out that x value is 26. So they're going to do 26 cars coming in, or they need to emit 26 cars a minute. So they need in 26 minutes, or they need to emit 26 cars per 1 minute, right? That's what they need to do. That's the ratio that they need to come in. Now the second part is asking, okay, well, if one attendant can handle 5.3, how many attendants is it going to take to maintain that 30-second rate? So I can just take 26 and divide it by divide it by 5.3, and we get 4.9-ish, something right there. So it's going to take about 5 attendants to maintain that 30-second time in line, I guess. So there's that problem for you.